Hi, I'm Kathy. In this lesson, we're going to look at exponential functions. Our specific objectives are real number exponents, graphs of exponential functions, exponential equations type 1, the number e, and compound interest. Let's start with a little bit of a discussion of real number exponents. What we want to do is extend the definition of a to the r for all real numbers r, or actually to all real numbers r. For example, suppose I wanted to evaluate 2 to the square root of 3. Now, the square root of 3 is an irrational number. The square root of 3 is approximately 1.732, but it goes on forever as an irrational number. So what does 2 to the square root of 3 mean, or how could we evaluate it? Well, we could approximate the square root of 3 with 1.7 and figure out 2 to the 1.7, and then figure out 2 to the 1.73, and then figure out 2 to the 1.732. And that way, the value of 2 to the 1.732 would be approaching and getting close to the actual value of 2 to the square root of 3, which is the thing we're interested in finding. Well, how would I evaluate any one of these? Let's look at 2 to the 1.7. I know that 1.7 is 1 and 7/10, or 17/10. And so I could make this, or maybe I should consider this 2 times 2 to the 7/10, and it's this part that can be considered 2 times the 10th root of 2 to the 7th power. I started to write a 7th there. And I can carry this, and this is something we know how to evaluate. It's a rational root, not an irrational root, and I can carry this idea through to all of these particular expressions and get closer and closer to the idea of 2 to the square root of 3. Well, that leads us to some additional properties of exponents. Let's look at those. For any real number a greater than 0 and not equal to 1, the following statements are true. A to the x is a unique real number for all real numbers x, which is what I was trying to illustrate. Then we also have a to the b equals a to the c if and only if b equals c. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. If a is a fraction between 0 and 1 and m is less than n, then a to the m is greater than a to the n. Let's look at just some quick examples of these three properties to make sure you understand them. One example that we might write down for property B is something like, if 3 to the x equals 3 to the 4th, then it must be true that x equals 4. That's an example of property B. And for property C, I can say something like 4 squared is less than 4 cubed. Notice that 4 corresponds to a in the property, and 4 is a number bigger than 1. So 4 to the 2nd power is less than 4 to the 3rd power. But to illustrate property D, I could say something like 1/2, a number between 0 and 1, squared, is bigger than 1/2 cubed. So if the base in an exponential expression is less than 1, greater than 0, that to the 2nd power is bigger than that thing to the 3rd power. Well, let's put all this discussion into a function. Let's look at the function f of x equal 2 to the x and make a graph of it by hand. In order to make a graph by hand, I'm going to come up with a table of values and plot some points. For x, I want to use the numbers -2, -1, 0, 1, and 2. If x is -2 in this function, I need to find 2 to the -2, which is 1/4, or 0.25. If x is -1, this is 2 to the -1, which is 1/2, or 0.5. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. Well, let's plot these points and come up with a graph of that function. I plot the point -2, positive a fourth, -1, a half, 0, 1, 1, 2, 2, 4, and I connect those points with a smooth curve, and I get the graph of the exponential function 2 to the x. Let's write down this function's domain and range. The domain of the function is from -infinity to +infinity. That's the x's. The range for the function is from 0, not including 0, to +infinity. And let's talk about that not including 0 part. This function gets closer and closer and closer to the x-axis but never touches it, which means that the x-axis is a horizontal asymptote. For the function, for of x equal 2 to the x. Well, that's one example of an exponential function. Let's summarize that information in the next couple of graphics. An exponential function of the form f of x equal a to the x, where a is bigger than 1, like the one we just drew, where a was 2, has domain -infinity to infinity, range 0 to infinity, and graph that looks like the one we graphed a minute ago. Notice that this graph contains the points -1, a to the -1, 0, 1, and 1a. Some other bits of information about that graph. The function a to the x for a greater than 1 is increasing and continuous on its entire domain. The x-axis is the horizontal asymptote as x goes to -infinity, and you saw that on our graph. The graph goes through these 3 points. Well, let's look at another general exponential function of the same form, f of x equal a to the x. But let's consider a to be between 0 and 1, a fraction between 0 and 1. The domain is still -infinity to infinity. The range is 0 to infinity. The graph looks a little different than the graph we graphed a few minutes ago. It does contain -1a to the -1, 0, 1, and 1a. And there's some other information we want to write down about this exponential function. So the function a to the x, where a is between 0 and 1, is decreasing and continuous on its domain. There's the domain. The x-axis is a horizontal asymptote, but this time as x goes to +infinity, the graph goes through these points, -1, a to the -1, 0, 1, and 1a. Well, let's use some of this information and work another example. What we want to do is explain how the graph of 2 to the x plus 5 minus 3 can be obtained from the graph of 2 to the x. And this is the one we graphed a few minutes ago. Then sketch a graph. As far as an explanation, I see that the graph is shifted 5 units to the left and 3 units down, or it is a shift of 5 to the left and 3 down of the graph of 2 to the x. Because it's shifted 3 units down, the horizontal asymptote is going to be the line y equal -3. Well, let's use that information to draw a graph. We want to draw the horizontal asymptote at y equal -3. Now the exponential function is also shifted 5 to the left. It contained originally the point 0, 1. That was shifted down 3, and now I need to shift it 5 to the left, and I'll go ahead and sketch a graph, but then I'm going to label that point. So here's a graph of the exponential function. This point that was for the non-shifted graph 0, 1 is the point -5, -2. And let me label my horizontal asymptote. Well, let's continue and look at some exponential equations. Here's what we want to do. We want to solve each of these exponential equations, and the first is 25 to the x equals 125. We're going to solve this using that property B for exponential exponents that we saw earlier. What I'm going to do is write each side as a power of the same base. 25 is 5 squared, and 5 squared to the x is 5 to the 2x. 125 is 5 to the third. If 5 to the 2x equals 5 to the third, then 2x must be 3, so x must be 3 over 2. The solution set for this equation is 3/2. If I were to check this one, what I would do is put 3/2 for x in the original equation and find 25 to the 3/2. I want to know, is that 125? Well, remember that 25 to the 3/2 means the square root of 25, which is 5, to the third power, which will give us 125. So that does check. Let's use a similar procedure to solve this equation. I see 1/3 to the x equals 81. Looking at the right-hand side, I know that 81 is 3 to the 4th, which gives me an idea of what I want to do with the left-hand side. 1/3 is 3 to the negative 1, and 3 to the negative 1 to the x is 3 to the negative x. If 3 to the negative x equals 3 to the 4th, it must be true that negative x is 4. So x is negative 4 is the solution. The solution set to the equation is the set containing negative 4. And I could check this as I did the previous one by substituting negative 4 into the original. Well, I'd like you to try a problem like this. Why don't you pause the video and work the following problem and restart when you're ready to check. Here's what I want you to do. Solve the equation 2 to the 3 minus y equals 8. Pause the video now. Well, let's see how you did. We have 2 to the 3 minus y equals 8. 8, I know, is 2 to the third. So my equation reads 2 to the 3 minus y equals 2 to the third. If that is true, it must be true that 3 minus y equals 3. And subtracting 3 from both sides, I see negative y is 0 or y is 0. The solution set is 0. Doing a quick check, I can put 0 for y in the original, and I get question mark. 2 to the third equals 8, or 8 equals 8, and my solution checks. Let's continue with our discussion of exponentials, talking about a special number, the number e. The number e is an irrational number. I'm going to show you the value of the number e by taking this expression 1 plus 1 over x to the x power and evaluating it for x's that get larger and larger. Starting with x to the first. Putting x to the first in here, I'd have 1 plus 1 to the first. 1 plus 1 is 2 to the first is 2. If I put 10 in there, I need to do 1 plus 1/10 to the 10th power. Let's use a calculator to help make some calculations here. What I want to find is 1 plus 1 divided by 10 all to the 10th power. That number's 2.59. Well, let's do all of that for x equal to 100. 1 plus 1 divided by 100 all to the 100th power. Now let's do that for x equal to 1,000. 1 plus 1 divided by 1,000 to the 1,000th power. And I can see, and we'll do one more calculation, that my numbers seem to be approaching some common amount. Let's do one more calculation for x equal to 10,000. 1 plus 1 divided by 10,000 all to the 10,000 power, 2.7181. Well, let's write these numbers down. 2.7181. And in our table, the numbers here are approaching the value of the number e. Now, as I said earlier, e is irrational, which means it's a non-repeating, non-terminating decimal. It's approximately 2.7181 and some other digits. So we'll say it's approximately 2.718. Well, let's look at a graph of a function y equal e to the x. E is the number 2.718. Let's again use a calculator to help make this graph. So on our calculator, locate your e function, put x as the exponent, and let's set a window of -5, 5 in the x direction, -5, 5 in the y direction, and push graph, and we get a graph that we can translate to our paper. Notice that the graph contains 0, 1. If x is 1, y is e. If x is -1, somewhere over here, y is e to the -1, or 1 over e. And we get a graph of the exponential function base e. Well, as a final item in this lesson, we want to talk about compound interest. Here's a formula. Suppose that a principal of $P is invested at an annual interest rate R in percent, compounded n times per year. Then the amount A accumulated after T years is given by the formula. A equals P times 1 plus R over n to the nt power. R is the annual interest rate, n is the number of compounding periods each year, and T is the time in years, P is the amount invested, and A is the amount in the account after T years. Let's try this formula. Suppose that $1,000 is invested at an annual interest rate of 8%, compounded quarterly. Find the total amount in the account after 10 years if no withdrawals are made. Well, our principal is 1,000, and we're interested in calculating A. So we put 1,000 for P times 1 plus the interest rate made into a decimal, 0.08, divided by the number of compounding periods. Now, if this is compounded quarterly, that's 4 times a year. And as an exponent, we have n times t, or the number of compounding periods times the number of years. Let's get the amount of money in the account on a calculator. So we'll go to our calculator, and we will find 1,000 times 1 plus 0.08 divided by 4, all of that to the 4 times 10, or 40th power. Now, rounding that so that it is reasonable for this problem, we're going to use $2,208.04. $2,208.04. Well, in this lesson, we've looked at exponential functions used a number of different places. Be sure to work lots of exercises from your textbook for practice.